Let's very briefly understand what the ML Engine's prediction service is all about. At the end of the training process, we have a serialized TensorFlow model. This was written out by our trainer package. This model can now be used as a model resource, a hosted resource that can be hit or accessed by RESTful API calls by other clients. Those clients can now invoke the functionality within that model, submitting JSON requests and getting back the prediction responses. And this functionality of making a model available as an endpoint for clients to hit, this is made available as a part of the ML Engine's prediction service. This is exactly what we are going to make use of right now. As an aside, you should know that there are actually two modes that one can use here. There is an online mode and a batch mode. The online or interactive mode is marked by a high rate of requests. Here, the ML engine is going to try and minimize latency. On the other hand, batch prediction jobs are typically invoked on large datasets, and their ML engine is going to try and minimize the total job running time. The inner workings of the ML engine are quite different in these two modes, but that is beyond the scope of this conversation. As far as interacting with the online mode goes, that's pretty simple. We already saw how we can submit JSON requests and get a result back. The batch mode is more involved. In any case, let's now turn our attention back to our data lab. Now that our training job has succeeded, we can go ahead and deploy our model. In order to do that, first let's find the actual name of the subdirectory. As before, the model would have been serialized to a directory with a large numeric string name. As we can see here, that string is 1513917472784. This is actually going to be made use of in the model location. This is one of the variables which we need in our bash script. Notice how that model location pipes the output of the gsutil ls command and saves it in the form of an environment variable. Notice also how it cleverly makes use of the tail -1 in order to make sure that it only picks up the one last directory name. In any case, in addition to this model location, we also initialize variables for the model name and the model version. The model name here is Taxifair and the model version is V1. Once that's done, we can go ahead and create a model. This we do with gcloud ML engine models create followed by the model name. Notice how we need to specify the region. This is the region in which our bucket is hosted. Once the model is created, we can go ahead and deploy a version of that particular model. Once again, this requires us to use gcloud ML engine versions create. Once we've deployed our model, we can go ahead and make use of it for prediction. This deployment process can take up to 5 minutes, by the way, as the code tells us. In any case, once the deployment is complete, we can now use it for prediction. This we will do in two different ways. The first is directly from the bash shell. Notice that the bash command that we invoked was gcloud ml engine predict, followed by the model name, which is Taxifair, the version, that's v1, and of course the JSON instances file. Here we will simply pass in the JSON instances file that we had already created. As before, we get the output of 11.5881. That's because even though we made use of the distributed training service, we still only used a very small data set. The real improvement in quality will come when we carry out the training with a much larger data set. In any case, let's now move on and take a look at a programmatic prediction call. This snippet of code that follows is going to carry out prediction using a RESTful API call. This is going to require us to carry out some authentication before we can access the API, and so we need to import the Google API client as well as the discovery service from within it, the auth2 client so that we can set up the Google credentials. Those will be required for us to access the API. If you've used the Google Cloud Platform a lot, you will be aware that there is an application default credential that is associated with a project. We go ahead and get that and save it in a variable called credentials. Then we create an API object. This is effectively obtained by the discovery of an ML API. So this is the ML engine. We are looking for the RESTful API endpoint corresponding to the ML engine version v1. notice that while doing so, we have to specify a discovery service URL as well as those application default credentials which we just instantiated. Then next we set up the request data. This is a JSON fragment in which we have an instances element. This is a list. Each element of that list represents one request for prediction. Here we just have the one element in our list. This one element has values for each of the X variables, that is the pickup and drop off latitudes and longitudes and the number of passengers. What follows next is the actual invocation of the RESTful API. Notice how we hit the API that we just obtained from the discovery service. So we call the predict method on that along with the JSON request data that we just instantiated. Hitting Shift Enter causes this response to be evaluated, and the response once again is 11.5881, just as we had a moment ago when we accessed the same API using the gcloud command line interface. Now, the whole point of actually using the ML engine for training in particular was in order to be able to train on a much larger data set. This is something which could take up a fair amount of time and money if we did it ourselves on the cloud, and so Google has very considerately done it for us. They have trained the machine learning model with 1 million rows, that is 100 times the size of the original dataset, and they have exported this data into cloud storage. Now, running the Cloud ML Engine API with this 1 million row training dataset is going to take quite a bit of time. It takes 60 minutes, and that is going to take quite a bit of time and money if we were to do it ourselves. Now, we would think that training a model on 1 million rows would lead to a much better performing model than training it on just 10,000 rows. But if we read closely the comments embedded in the markdown, we can see that this is actually not the case. The RMSE was basically unchanged. As the author says, it remains stubbornly at 9.03. So simply adding more data did not actually help. In the remaining portion of this module, we shall make some pretty fundamental changes to the model. We will change the manner in which we calculate the features, those are the X variables, and we shall see that when we combine that feature engineering along with a much larger training data set, we do actually get a dramatic improvement in our model. But from this exercise so far, we can see that just scaling up, just using a much larger data set along with distributed training on the cloud, in and of itself is not necessarily going to give us a magically better result.